Hello there, and welcome to the Sleepless Scientist Night. I'm so glad you found your way here tonight. Space travel, the dream of reaching beyond our world, has captivated humanity for generations. Tonight, drift gently through the cosmos, exploring the science, the challenges, and the quiet beauty of journeying beyond Earth. Wherever you are right now, perhaps with the windows closed against the cold, or with the gentle sound of rain outside, allow yourself to settle into this shared moment of stillness. Tonight, explore 100 remarkable truths about space travel, from the violent thrust of rocket launches to the serene silence of orbital flight, from the fragility of human bodies in microgravity to the resilience of spacecraft crossing billions of kilometers, from the dreams of colonizing Mars to the reality of living aboard the International Space Station. If this quiet exploration of the cosmos helps you unwind, a gentle like and subscribe helps other stargazers find their way here too. It only takes a moment, but it means the universe to us. One sleepy soul at a time. For now, you don't need to do anything at all. Just let your shoulders soften. Let your breathing fall into its own rhythm. Imagine yourself drifting in a space of gentle curiosity, where facts become stories and stories become dreams. If you'd like, close your eyes and take a deep breath. Imagine you're lying in a small spacecraft, drifting gently through the endless night sky, moving without boundaries, without destination, only the light of distant stars and absolute silence. Let go of all limits. Let your mind drift through infinite space. And when you're ready, begin. Space is closer than you think. The boundary between Earth's atmosphere and space, called the Kármán line, sits just 100 kilometers above sea level. That's roughly the distance between two neighboring cities. If you could drive straight up at highway speed, you'd reach space in about an hour. Yet crossing this boundary requires enormous energy. Earth's gravity pulls everything downward with relentless force. Rockets must accelerate to at least 7.9 kilometers per second, or about 28,000 kilometers per hour, just to achieve orbit. This velocity, called orbital velocity, allows spacecraft to fall toward Earth continuously, while simultaneously moving forward fast enough that they keep missing it, tracing a circular or elliptical path around the planet. Without reaching this speed, any object launched upward will simply arc back down, pulled by gravity's patient grip. Thousands of satellites orbit Earth right now. As of 2025, more than 1,500 active satellites circle our planet, serving countless purposes. Communication satellites relay television signals, internet data, and phone calls across continents. Navigation satellites like those in the GPS constellation help billions of people find their way. Weather satellites monitor storms, track climate patterns, and provide early warnings for severe weather. Scientific satellites study Earth's environment, observe distant galaxies, and conduct experiments in microgravity. Each satellite follows a carefully calculated path, maintained by occasional thruster firings to counteract atmospheric drag and gravitational perturbations. This orbital infrastructure, invisible from ground level, has become essential to modern civilization, quietly enabling technologies we use every day without thinking about the machinery floating overhead. The International Space Station orbits at about 400 kilometers altitude, completing one full orbit every 90 minutes. Traveling at approximately 7.7 kilometers per second, faster than a speeding bullet. The station experiences sunrise and sunset 16 times per day. Astronauts aboard see Earth's horizon constantly changing, watching continents drift past. Oceans gleam in sunlight. Clouds swirl in mesmerizing patterns. At this altitude, Earth's atmosphere is thin, but not absent. Residual air molecules create tiny amounts of drag, gradually slowing the station. Without regular reboosts from visiting spacecraft or the station's own thrusters, it would slowly spiral downward, eventually re-entering the atmosphere and burning up. This delicate balance between gravity pulling down and forward motion, keeping the station aloft, requires constant attention. Small adjustments, ongoing maintenance. Living in space for months reveals how adapted humans are to Earth's gravity. Auroras, those shimmering curtains of light in polar skies, result from charged particles from the sun interacting with Earth's magnetic field and atmosphere. Solar wind, a stream of electrons and protons constantly flowing from the sun, reaches Earth and is mostly deflected by our planet's magnetic field, but near the poles, where magnetic field lines converge and dip toward the surface. Some particles follow these lines downward into the upper atmosphere. When these energetic particles collide with oxygen and nitrogen molecules in the air, they transfer energy, causing the gases to glow. Oxygen produces green and red light. Nitrogen creates blue and purple hues. From space, astronauts see auroras from above, glowing bands wrapped around Earth's poles like ethereal crowns. These lights, beautiful from any perspective, remind us that Earth exists within the Sun's extended atmosphere, constantly bathed in stellar wind, protected by invisible magnetic shields generated by our planet's churning iron core. Rocket launches are controlled explosions. Chemical rockets burn fuel and oxidizer in a combustion chamber, producing hot gases that expand rapidly. These gases are channeled through a nozzle, converting thermal energy into kinetic energy, accelerating the exhaust to hypersonic speeds. Newton's third law governs the process. For every action, there is an equal and opposite reaction. As exhaust shoots downward at tremendous velocity, the rocket is pushed upward with equal force. Most of a rocket's mass at launch is fuel. The Saturn V rocket that carried Apollo astronauts to the moon weighed about 3,000 metric tons at liftoff, but only about 40 metric tons reached orbit. The rest was fuel and discarded rocket stages. This tyranny of the rocket equation, as engineers call it, makes space travel expensive and challenging. Every kilogram of payload requires many kilograms of fuel, which itself requires fuel to lift, creating a cascade of requirements that makes even small payloads costly to launch. Starship, SpaceX's fully reusable launch vehicle under development, represents an ambitious attempt to revolutionize space transportation. Standing approximately 121 meters tall, when fully stacked, it's designed to carry up to 100 metric tons to orbit, potentially more than any current launcher. The vehicle uses stainless steel construction, unusual for rockets, chosen for its strength, durability, and ability to withstand extreme temperatures during both ascent and re-entry. Most revolutionary is the goal of full reusability. Both the Super Heavy booster and the Starship upper stage are designed to land and fly again, potentially with minimal refurbishment between flights. SpaceX envisions Starship carrying cargo and crew to Mars, supporting lunar landings for the Artemis program, perhaps eventually enabling point-to-point Earth transportation, flying passengers anywhere on Earth in under an hour. However, as of early 2025, Starship has not yet completed a full orbital mission with successful landing and reuse. Development continues, with each test flight revealing new challenges and solutions, demonstrating the immense difficulty of making spaceflight routine and affordable. Weightlessness is actually freefall. Astronauts aboard the International Space Station aren't beyond Earth's gravity. They're falling toward Earth constantly. But they're also moving forward so fast that they keep missing the planet, continuously falling around Earth rather than into it. This state of perpetual freefall creates the sensation of weightlessness. Inside the station, everything, astronauts, equipment, water droplets, falls together at the same rate. So, relative to each other, nothing appears to fall at all. This microgravity environment, technically not zero gravity but extremely weak gravity, profoundly affects human physiology. Without gravity's constant downward pull, fluids in the body redistribute upward, causing puffy faces and stuffy sinuses. Bones lose density without weight, bearing stress. Muscles atrophy without resistance to work against. The cardiovascular system adapts to pumping blood without fighting gravity's pull downward. Long-duration space missions require extensive exercise regimens, hours daily on treadmills and resistance machines, to slow these changes. Even with exercise, astronauts returning from 6-month missions need weeks or months to fully readapt to Earth's gravity, their bodies having partially forgotten how to function in the environment that shaped human evolution. The Moon is Earth's only natural satellite, a companion world that has orbited our planet for over 4 billion years. Astronaut urine is recycled into drinking water aboard the International Space Station. This might sound unpleasant, but it's remarkable engineering achievement and practical necessity. Water is heavy. Launching water from Earth costs thousands of dollars per kilogram. For long-duration missions, carrying enough water from Earth isn't practical. Instead, the station's environmental control and life support system captures moisture from the air, including humidity from breathing, sweat evaporating from skin, and yes, water vapor from urine. Advanced filtration and purification processes remove contaminants, using a series of filters, chemical treatments, and distillation. The resulting water is cleaner than most tap water on Earth, tested constantly to ensure safety. Astronauts joke that today's coffee is tomorrow's coffee. The system achieves about 93% recovery of water, meaning very little is lost. For future missions to Mars, which might last 2 to 3 years, such closed-loop life support systems are essential. There's no resupply from Earth during the journey. Every molecule must be recycled, conserved, used as efficiently as possible, making spacecraft into tiny self-contained ecosystems where nothing can be wasted. Spacesuits are personal spacecraft. They provide oxygen to breathe, remove carbon dioxide exhaled, regulate temperature, shield against solar and cosmic radiation, protect from micrometeoroids, maintain pressure around the body, preventing fluids from boiling in space's vacuum. Modern spacesuits used for extravehicular activities, spacewalks, are marvels of engineering. Each suit costs millions of dollars and requires extensive maintenance. Inside, astronauts wear liquid cooling garments, underwear laced with tubes circulating chilled water to remove body heat, which can't dissipate through convection in vacuum. The suit's outer layers are made from multiple materials, each serving specific purpose: protecting against tears, providing insulation, reflecting solar heat, resisting radiation. Gloves are particularly challenging to design. They must be flexible enough for delicate work, repairing equipment, handling tools, yet strong enough to maintain pressure and protect hands. Astronauts report that working in pressurized gloves for hours is exhausting, like constantly squeezing a tennis ball. During spacewalks, lasting 6 to 8 hours, astronauts cannot eat, can sip water from a straw inside the helmet, must manage bodily functions using absorbent garments. It's physically demanding, mentally exhausting work, performed while floating in vacuum where any mistake could be fatal. The speed of light seems instantaneous on Earth. Light travels about 300,000 kilometers per second. Across a room, light arrives essentially immediately. Even across continents, light traveling through fiber optic cables takes only fractions of a second. But in space, distances are vast, and light's speed becomes a noticeable limitation. Light from the Moon takes about 1.3 seconds to reach Earth. Radio signals to and from the International Space Station have almost imperceptible delay. But Mars, depending on orbital positions, is between about 5 and 20 light minutes away. Commands sent to Mars rovers take minutes to arrive. Responses take additional minutes to return. This communication delay makes real-time remote control impossible. Rover drivers on Earth can't steer interactively. Instead, they upload sequences of commands, then wait to see results. Conversations with astronauts on Mars will have significant pauses between question and answer. For missions to outer solar system, delays stretch to hours. Voyager 1, now beyond the solar system's edge, takes over 22 hours for signals to reach Earth. This light speed barrier is fundamental. No information can travel faster. For humanity's expansion into space, delay is unavoidable reality, requiring new communication strategies, increased autonomy for distant spacecraft, patience from mission controllers, watching events that happened minutes or hours ago. Mars is the most Earth-like planet in our solar system, yet profoundly hostile to human life. Its atmosphere is about 1%, as thick as Earth's, mostly carbon dioxide, providing almost no pressure and no breathable oxygen. Temperatures average -60 degrees Celsius, though they can reach about 20 degrees Celsius at the equator during summer days, then plunge to -100 degrees Celsius at night. Solar radiation bathes the surface unimpeded by any protective magnetic field or thick atmosphere. Dust storms can engulf the entire planet for months. The soil contains perchlorates, toxic chemicals that could harm humans. Yet Mars is relatively accessible. Launch windows occur every 26 months, when Earth and Mars are favorably aligned. The journey takes about 6 to 9 months with current propulsion technology. Mars has water ice at its poles and beneath the surface, potential resource for future settlers. Its day is 24.6 hours long, similar to Earth's, making adaptation easier. Gravity is about 38% of Earth's, at enough to avoid the worst effects of microgravity, but still requiring adaptation. Despite these challenges, multiple space agencies and private companies are planning crewed Mars missions. NASA's Artemis program aims to establish sustainable lunar presence first, testing technologies and procedures for eventual Mars missions. Getting to Mars is hard. Surviving there is harder. Establishing permanent settlement is one of the greatest challenges humanity has ever contemplated, requiring solutions to countless engineering, biological, psychological, and logistical problems. Radiation in space comes from multiple sources, each presenting unique hazards. Solar radiation from the sun includes ultraviolet light, X-rays, and energetic particles. Solar flares and coronal mass ejections can release massive bursts of radiation. Galactic cosmic rays, high-energy particles from distant supernovae and other cosmic sources, constantly bombard spacecraft. These particles can penetrate spacecraft hulls, spacesuits, even human tissue, damaging DNA, increasing cancer risk, potentially causing acute radiation sickness during intense events. Earth's magnetic field and thick atmosphere protect us from most of this radiation. In low Earth orbit, astronauts aboard the ISS still receive some protection from Earth's magnetic field, though radiation exposure is higher than on surface. Beyond Earth's protective bubble, radiation exposure increases significantly. Moon has no magnetic field or atmosphere. Mars has neither magnetic field nor substantial atmosphere. Future deep space missions will require better shielding. Water, surprisingly, is excellent radiation shield. Some designs propose surrounding crew quarters with water tanks, providing both necessary resource and protective barrier. On long journeys to Mars or beyond, radiation exposure could accumulate to dangerous levels. Faster propulsion systems could reduce transit time, limiting exposure. Underground habitats on Moon or Mars would provide natural shielding from surface radiation. Managing radiation risk is a crucial challenge for long-duration space exploration, balancing protection against mass constraints. Cost, practicality. The Van Allen radiation belts are zones of charged particles trapped by Earth's magnetic field, encircling the planet like invisible donuts. There are two main belts, an inner belt and an outer belt, with a gap between them. The inner belt, mostly protons, extends from about 1,000 to 6,000 kilometers altitude. The outer belt, mostly electrons, extends from about 13,000 to 60,000 kilometers altitude. These belts are hazardous to spacecraft and astronauts. Prolonged exposure can damage electronics, degrade solar panels, harm biological tissue. Satellites operating in these regions require radiation-hardened components. The International Space Station orbits below the inner belt, avoiding most radiation. Apollo missions to the Moon passed through the belts quickly, limiting exposure. Mission planners carefully timed trajectories to minimize time in the most intense regions. Modern spacecraft heading beyond Earth orbit must either pass through quickly or take trajectories that avoid the worst areas. The belt's intensity varies with solar activity. During solar maximum, when the sun is most active, the belts become more intense. During solar minimum, they weaken somewhat. Understanding the Van Allen belts. named after physicist James Van Allen, who discovered them using early satellite data in 1958, is essential for planning any mission beyond low Earth orbit, balancing trajectory efficiency against radiation exposure in regions where Earth's magnetic field becomes both shield and trap. Orbital debris, also called space junk, is a growing problem. Thousands of defunct satellites, spent rocket stages, fragments from collisions and explosions orbit Earth at velocities of several kilometers per second. At these speeds, even tiny paint flecks carry enough energy to damage spacecraft. Larger debris could catastrophically destroy satellites or endanger astronauts. More than 34,000 pieces of debris, larger than 10 centimeters, are tracked. Hundreds of thousands of smaller pieces exist, but can't be monitored individually. Space station occasionally must perform debris avoidance maneuvers, adjusting its orbit to dodge tracked objects. Satellites have been lost to debris impacts. In 2009, an inactive Russian satellite collided with an operational American communications satellite, creating thousands of new debris fragments. This growing cloud of junk threatens future space activities. Each collision creates more debris, potentially triggering cascade effect called Kessler syndrome, where debris collisions create more debris, which cause more collisions, exponentially increasing the problem until certain orbital regions become unusable, too dangerous for spacecraft to operate. Mitigation efforts include designing satellites to deorbit safely at end of life, developing technologies to remove defunct satellites, international agreements to minimize new debris creation. Some companies are developing space cleanup missions, spacecraft designed to capture and deorbit large debris pieces. The challenge is immense and growing. Space, once seemingly infinite and empty, is becoming cluttered commons, requiring careful stewardship to preserve access for future generations who will depend on satellites for communication, navigation, weather forecasting, Earth observation, scientific research. Re-entry is violence and fire. When spacecraft return to Earth, they must shed enormous orbital velocity, rather than using rockets to slow down, which would require prohibitive amounts of fuel. Spacecraft use Earth's atmosphere as brake. As spacecraft descends into thicker air, friction with atmospheric molecules creates intense heat. Re-entry temperatures can exceed 1500 degrees Celsius, hot enough to melt most materials. Spacecraft are protected by heat shields, ablative materials designed to slowly burn away, carrying heat away from the vehicle. The space shuttle used ceramic tiles that could withstand extreme temperatures repeatedly. Modern capsules like SpaceX's Dragon use Pica X, phenolic impregnated carbon ablator, a material that chars and vaporizes in controlled manner, protecting the capsule's interior. During re-entry, plasma forms around the spacecraft, superheated ionized gas, glowing bright orange and white. This plasma temporarily blocks radio communications, creating blackout period when ground controllers cannot contact the returning crew. Astronauts experience significant G-forces as atmospheric drag decelerates the spacecraft from orbital velocity to subsonic speeds. Peak deceleration can reach 4 to 5 gs, pressing astronauts firmly into their seats, making breathing difficult, vision narrowed. Re-entry is among the most dangerous phases of spaceflight. Heat shield failure is catastrophic. As demonstrated by Space Shuttle, Columbia disaster in 2003, when damaged thermal protection system allowed hot gases to penetrate the wing, destroying the vehicle and killing the crew. Every successful re-entry is testament to careful engineering, precise calculations, robust testing, and a bit of luck. The Artemis program aims to return humans to the moon and establish sustainable presence. Named after Greek goddess of moon and twin sister of Apollo, Artemis represents NASA's next chapter in lunar exploration. Unlike Apollo, which conducted brief surface missions and then departed, Artemis plans long-term presence. The program includes Lunar Gateway, a small space station in lunar orbit, serving as staging point for surface missions. Artemis missions will explore lunar South Pole, where permanently shadowed craters may contain water ice, valuable resource for life support and rocket fuel production. Artemis 1, an uncrewed test flight of the Space Launch System rocket and Orion spacecraft, successfully flew around the Moon in late 2022. Artemis 2 will carry astronauts on lunar flyby, currently scheduled for no earlier than mid-2026. Artemis 3 aims to land astronauts on the Moon, including the first woman and the first person of color to walk on the lunar surface, currently scheduled for no earlier than September 2026, though delays are possible. The program represents international collaboration, with contributions from European Space Agency, Canadian Space Agency, Japan Aerospace Exploration Agency, and others. Artemis is also foundation for eventual Mars missions. Technologies, procedures, and experience gained from establishing lunar presence will inform how we approach Mars exploration. The Moon is testing ground, close enough that help from Earth is only days away, yet far enough to challenge us with isolation, radiation, resource scarcity, and the harsh realities of living beyond Earth's protective embrace. Ion engines are different from chemical rockets. Instead of burning fuel in explosive combustion, ion engines use electricity, typically from solar panels, to accelerate ions, charged atoms, to very high velocities using electromagnetic fields. The thrust produced is tiny, measured in millinewtons, roughly equivalent to weight of a sheet of paper on your hand. A chemical rocket can produce millions of newtons of thrust, but ion engines are incredibly efficient. They can operate continuously for months or years, gradually accelerating spacecraft to very high velocities without carrying massive amounts of fuel. Chemical rockets expend enormous fuel for brief periods of thrust. Ion engines sip fuel slowly but steadily, achieving higher final velocities with less propellant mass. NASA's Dawn spacecraft used ion propulsion to visit asteroid Vesta and dwarf planet Ceres. Missions impossible with chemical rockets due to the propellant mass that would have been required. The technology is quiet, smooth, elegant in its simplicity. There's no violence, no explosions, just gentle, persistent push accumulating over time. For future missions to outer solar system, asteroid mining operations, long-duration cargo missions to Mars, ion engines offer advantages. They're not suitable for launching from planetary surfaces, where high thrust is needed to overcome gravity. But in the vacuum of space, where there's no resistance, patient acceleration is often better strategy than brief, violent burns. Ion propulsion represents different philosophy of space travel, trading immediacy for efficiency, force for endurance, embracing the patient accumulation of velocity across the silent months and years of interplanetary journeys. Microgravity affects the human body in unexpected ways. Fluid redistribution causes faces to puff up, sinuses to feel congested, giving astronauts the characteristic puffy appearance often seen in space photos. Without gravity pulling blood downward toward legs, cardiovascular system recalibrates. Heart shrinks slightly since it doesn't need to work as hard, pumping blood upward. Bone density decreases, approximately 1 to 2% per month in weight-bearing bones like hips, spine, legs. This is similar to osteoporosis, but happening much faster. Bones constantly remodel throughout life, breaking down old bone and building new bone. On Earth, mechanical stress, from supporting body weight signals, bones to maintain strength. In microgravity, this stress disappears. Bones lose mass without rebuilding at the same rate. Astronauts' urine becomes calcium-rich as bone breaks down. Muscles, especially those used for posture and walking, atrophy without regular resistance. Leg muscles, back muscles, core muscles weaken noticeably after weeks in space. The spine lengthens slightly as gravity no longer compresses vertebrae, making astronauts about 2 inches taller in space. This can cause back pain as spine adjusts. Vision changes affect some astronauts. Fluid shift causes pressure on the back of the eyeball, slightly flattening it, affecting vision. Some astronauts develop permanent vision changes after long-duration missions. The immune system weakens, making astronauts more susceptible to infections. Wound healing slows. Radiation exposure increases cancer risk over time. To counteract these effects, astronauts exercise about 2 hours daily, using specially designed equipment that creates resistance in weightlessness. They take vitamin D supplements since there's no sunlight exposure inside the station except through small windows. Returning to Earth requires readaptation. Astronauts feel very heavy, struggle to walk, experience dizziness and balance problems for days or weeks. Long-duration missions to Mars will face these challenges intensified. 6 to 9 months in transit, time on Mars with only 38% Earth gravity, then another 6 to 9 months returning. Human bodies evolved for Earth's gravity. Living elsewhere requires constant countermeasures, vigilant monitoring, and acceptance that space travel changes us in ways both subtle and profound. Water is crucial for space exploration. Human bodies are mostly water. We need water to drink, wash, prepare food, maintain hygiene. Water is also heavy, about 1 kilogram per liter, making it expensive to launch from Earth. On the Moon and Mars, water ice exists beneath the surface and in permanently shadowed craters near the poles. Finding and utilizing this water is priority for future missions. Water can be split into hydrogen and oxygen through electrolysis. Oxygen for breathing, hydrogen and oxygen combined as rocket fuel. Water shields radiation better than most materials. Future habitats might be surrounded by water tanks, providing both life support and protection. Water can be used for growing plants in greenhouses, enabling partial food self-sufficiency. The presence of water ice on the Moon makes lunar bases more feasible. Instead of transporting all water from Earth, future colonists can extract local water, process it, use it. This concept, in situ resource utilization, is key to making space settlement economically viable. Every kilogram extracted locally is 1 kilogram not launched from Earth, saving thousands of dollars. Mars has frozen water at its poles, subsurface ice in mid-latitudes, possibly seasonal liquid brines in certain conditions. Accessing this water, purifying it, storing it will be among the first tasks for any Mars settlement. Water, mundane on Earth, becomes precious resource in space, a foundation for human presence, enabler of agriculture, source of propellant for vehicles departing for deeper space. Learning to find water, extract it, conserve it, recycle it, transforms how we think about exploration. Space travel is not just about reaching destinations, but about understanding how to live sustainably with local resources, adapting to environments where resupply from Earth is impossible or prohibitively expensive. The James Webb Space Telescope, launched in December 2021, has revolutionized our understanding of the universe. Positioned at the second Lagrange point, about 1.5 million kilometers from Earth, Webb observes the universe in infrared wavelengths, seeing through dust clouds that block visible light, detecting heat from distant galaxies formed billions of years ago. Its 18 hexagonal mirror segments, coated in gold to reflect infrared light, work together as a 6.5-meter diameter primary mirror, much larger than Hubble's 2.4-meter mirror. A tennis court-sized sunshield keeps the telescope cold enough to detect faint infrared signals without interference from its own heat. Webb has captured images of the earliest galaxies, formed just a few 100 million years after the Big Bang. It's studying exoplanet atmospheres, detecting molecules like water vapor and carbon dioxide in the air of planets orbiting distant stars. It's observing star formation within nebulae, planetary systems forming around young stars, and investigating dark matter and dark energy that dominate the universe. The telescope represents international collaboration, built by NASA with contributions from European Space Agency and Canadian Space Agency. Its observations are expanding our understanding of cosmic history, the nature of galaxies, the possibility of life beyond Earth. Webb's infrared vision allows it to see what visible light telescopes cannot, revealing hidden structures, ancient light, and phenomena invisible to human eyes. Each image Webb sends back is a window into the deep past, light that traveled for billions of years across expanding space to reach this carefully positioned machine, silently watching the universe unfold. Gravity assists, also called gravitational slingshots, allow spacecraft to change velocity and direction using planets' gravity and motion. As spacecraft approaches planets, gravity pulls it, accelerating it. If trajectory is carefully planned, spacecraft can swing around planets' backside, stealing tiny bit of planet's orbital momentum. The spacecraft speeds up significantly relative to the Sun, while planet slows down imperceptibly, mass too large for the effect to be noticeable. This technique enabled Voyager missions to visit multiple planets using relatively little fuel. Voyager 2 visited Jupiter, Saturn, Uranus, and Neptune, a grand tour possible only because planets aligned favorably in a configuration that occurs once every 176 years. Each planetary flyby gave Voyager a boost, increasing speed enough to reach the next target. Without gravity assists, these missions would have required far more fuel, making them impractical with available rocket technology. Modern missions routinely use gravity assists. The Parker Solar Probe uses Venus repeatedly to adjust its orbit, diving closer to the Sun with each pass. Juno mission used Earth gravity assist to reach Jupiter. The technique is elegant application of orbital mechanics, using natural motions of planets to provide free acceleration. It requires precise calculations, launching at exactly the right time, hitting narrow trajectory windows with minimal error. Mistakes can't be easily corrected. Missing a gravity assist might mean mission failure, but when executed successfully, gravity assists transform impossible missions into achievable ones, allowing spacecraft to reach destinations and speeds unattainable through rocket thrust alone. The physics is deterministic, perfectly predictable, yet still feels like magic. Borrowing energy from planets' motion, navigating solar system with balletic precision. Space food has come a long way since early days. Mercury astronauts ate paste squeezed from tubes, unappetizing but functional. Gemini and Apollo astronauts had freeze-dried meals, rehydrated with water, still bland but more varied. Today's space food includes hundreds of options, from freeze-dried shrimp cocktail, a favorite of many astronauts, to thermostabilized beef stew, irradiated meat, fresh fruit and vegetables delivered by cargo ships. Food must meet strict requirements: long shelf life without refrigeration, minimal crumbs that could float and damage equipment, packaging that doesn't take much space or create excessive waste. Astronauts eat from pouches and trays, using utensils that work in weightlessness. Liquids are drunk through straws from sealed pouches. Salt and pepper come in liquid form since grains would float away. Taste perception changes slightly in microgravity due to fluid shift and congestion, making food taste blander. Astronauts often request extra spices and hot sauce to enhance flavor. Mealtimes are important for crew morale. Opportunities to gather, share food, maintain some normalcy. International partners contribute foods from their cuisines: Russian borscht, Japanese ramen, European dishes, American barbecue, creating diverse menu. For future long-duration missions to Mars, food systems will need to be even more robust. Cargo mass is limited. Growing food hydroponically or in greenhouses becomes an attractive option, providing fresh produce, improving air quality, boosting psychological well-being. Research on space agriculture continues aboard the ISS. Growing lettuce, radishes, peppers, testing techniques for larger-scale cultivation. Eating is fundamental human activity. In space, it becomes engineering challenge, logistical puzzle, cultural touchstone, reminder of home, comfort in alien environment. Mastering food production in space is step towards self-sufficiency, a key to permanent presence beyond Earth. The Moon's surface is covered in regolith, a layer of loose, fragmented material created by billions of years of meteorite impacts. Unlike Earth soil, which contains organic matter and moisture, lunar regolith is bone dry, consists of fine dust and jagged rock fragments, and has been pulverized by countless impacts without weathering by water or wind. The dust is electrostatically charged due to solar radiation, causing it to cling stubbornly to spacesuits, equipment, and anything else it touches. Apollo astronauts found the dust got into everything: jamming mechanisms, scratching visors, infiltrating seals despite precautions. It smelled like spent gunpowder when brought inside the lunar module. One described it as the scent of a firing range. The fine particles irritated lungs and sinuses, raising concerns about long-term health effects. Future lunar missions must develop dust-resistant technologies. Some proposals suggest leaving spacesuits in airlocks rather than bringing them inside habitats. Engineers are designing seals, materials, and cleaning systems that resist or remove dust more effectively. Dust might seem like a minor annoyance compared to radiation or temperature extremes, but persistent problems, ones affecting every activity, sometimes prove more troublesome than dramatic dangers. Living with lunar dust will be a daily challenge for anyone working on the moon, requiring constant attention, innovative solutions, acceptance that perfection is impossible in such fine-grained, clingy, abrasive environment. Saturn's rings, though visually stunning, are surprisingly thin. They span over 280,000 kilometers in diameter, but only about 10 meters thick in most places, making them proportionally thinner than paper. Rings consist mainly of water-ice particles, ranging from sand grain size to house-sized chunks, all orbiting Saturn in carefully organized bands. Complex gravitational interactions with Saturn's moons create gaps in the rings, regions where particles have been cleared out by resonant orbits. Rings aren't permanent features. They're relatively young, perhaps only 100 million years old, and are gradually falling into Saturn, destined to disappear in another 100 million years or so. We're fortunate to exist during the brief cosmic moment when Saturn wears this magnificent crown. The rings might have formed from a shattered moon or captured comet torn apart by Saturn's gravity. Their origin remains debated. What's certain is that they're beautiful, ephemeral on cosmic timescales, a reminder that even the most striking features of our solar system are temporary, changing, evolving across deep time. Starship, SpaceX's fully reusable Super Heavy launch vehicle, stands approximately 121 meters tall when fully stacked, making it the tallest rocket system ever built. It's designed to carry up to 100 metric tons to orbit, significantly more than any current launcher. Starship's stainless steel construction, unusual for rockets, provides strength while withstanding temperature extremes. Most revolutionary aspect is full reusability. Both Super Heavy booster and Starship upper stage are designed to land and fly again, dramatically reducing launch costs. SpaceX envisions Starship carrying cargo and crew to Mars, supporting lunar landings for Artemis program, perhaps eventually enabling point-to-point Earth transportation, flying passengers anywhere on Earth in under an hour. Ambitious vision, but testing continues, each flight revealing challenges and solutions. As of early 2025, the system has not yet achieved full operational capability. Redshift, the stretching of light wavelengths from objects moving away from us, provides crucial evidence for universe's expansion. Distant galaxies show light shifted toward red end of spectrum, indicating they're receding from us. More distant galaxies show greater red shift, meaning they're moving away faster. This relationship, discovered by Edwin Hubble in 1920s, revealed universe isn't static, but expanding, with space itself stretching, carrying galaxies apart. Observation revolutionized cosmology, suggesting universe had beginning, what we now call Big Bang. Every galaxy we see is moving away, making space travel beyond our local galactic group eventually impossible. Separated by expanding space, growing faster than light speed. The universe's expansion is accelerating, driven by mysterious dark energy. Distant future, billions of years from now, galaxies beyond our local group will fade from view, their light unable to reach us across ever-expanding space. Future civilizations will see emptier sky, evidence of cosmic expansion literally disappearing. We live in special time, able to observe distant universe, gather evidence about cosmic history. This window won't remain open forever. Curiosity rover discovered organic molecules on Mars, carbon-based compounds that are building blocks of life. Finding doesn't prove past life existed on Mars. Organic molecules can form through non-biological processes. But it demonstrates Mars once had chemical ingredients necessary for life. Combined with evidence of ancient lakes and rivers, discovery paints a picture of Mars billions of years ago, when it was warmer, wetter, potentially habitable. Whether Mars actually hosted life remains unknown. Perseverance rover is currently collecting samples from ancient river delta, selecting rocks most likely to preserve signs of past microbial life. These samples will eventually be returned to Earth for analysis in laboratories far more sophisticated than anything we can send to Mars. The Mars Sample Return Mission, a collaboration between NASA and European Space Agency, aims to bring these samples back in early 2030. Analyzing Martian rocks with full laboratory capabilities could finally answer whether life ever existed on Mars. Even if Mars never had life, studying its geology, climate history, and chemical evolution helps us understand planetary habitability. Why Earth became living world while Mars became frozen desert. Micrometeoroids, tiny space debris particles, smaller than grain of sand, constantly bombard spacecraft at orbital velocities. Even these tiny particles carry significant energy, capable of pitting metal, cracking glass, damaging solar panels. International Space Station's exterior shows countless tiny impact craters from micrometeoroids and paint flecks from other spacecraft. Most impacts cause only minor damage, but statistical probability of catastrophic impact increases with time. Space Station has multiple-layer hull, providing protection. Outer layers, designed to shatter incoming particles. Inner layers, stopping fragments. Windows have protective shutters closed when not in use. Future spacecraft, especially ones making multi-year journeys to Mars and beyond, must be designed to withstand thousands of micrometeoroid impacts over their operational lifetimes without critical system failures. The constant barrage is a reminder that space, though seemingly empty, is filled with hazards traveling at deadly speeds. Ganymede, Jupiter's largest moon, is larger than planet Mercury. It's the only moon known to have its own magnetic field, generated by liquid iron core beneath icy surface. Like Europa, Ganymede likely harbors subsurface ocean beneath ice shell. Ocean that might contain more water than Earth's oceans. But Ganymede's ocean is sandwiched between layers of ice, making it less accessible than Europa's ocean, which appears to have direct contact with rocky seafloor. Still, any world with liquid water deserves attention in search for life. Jupiter's system contains multiple potentially habitable moons, each with unique characteristics, collectively representing most promising places to search for life beyond Earth in our solar system. Future missions might send probes to drill through ice shells, deploy submarines to explore these alien oceans, search for life in environments utterly unlike anywhere on Earth's surface, yet perhaps similar to deep-sea vents, where life thrives in darkness, nourished by chemical energy rather than sunlight. Rocket nozzles are marvels of thermodynamics. They convert hot, high-pressure gases from combustion into high-velocity exhaust, generating thrust through Newton's third law. Nozzle shape is critical, carefully designed to expand gases efficiently, maximizing velocity while minimizing turbulence. At sea level, nozzles optimized for atmospheric pressure. But in vacuum of space, different. Nozzle geometry works better. Some advanced engines use extendable nozzles that are compact during launch, then extend once in space for improved efficiency. Nozzles must withstand extreme temperatures, cooled by circulating fuel through channels in nozzle walls before burning it. This regenerative cooling prevents nozzles from melting, turning potential waste into useful preheating of propellants. Every aspect of rocket design reflects generations of accumulated engineering wisdom, solving problems that killed early pioneers. The development of reliable, efficient rockets required decades of trial and error, explosions, failures, gradual refinement. Each modern rocket launch is legacy of that difficult journey. Black holes aren't actually holes, but regions where gravity is so intense that nothing, not even light, can escape once passing event horizon boundary. Matter falling toward black hole doesn't disappear, but gets compressed, eventually adding to black hole's mass. From outside, black hole appears as dark sphere surrounded by accretion disk, swirling matter, glowing intensely as it spirals inward. Time near event horizon passes slower due to extreme gravitational time dilation. Theoretical spaceship hovering near event horizon would experience time passing much slower than distant observers. Black holes challenge our understanding of physics, places where Einstein's relativity meets quantum mechanics, producing paradoxes we're still working to resolve. What happens to information that falls into black hole? Does it disappear, violating quantum mechanics? Or is it somehow preserved? These questions remain at frontier of theoretical physics. Black holes aren't just cosmic oddities, but laboratories for understanding nature's most extreme conditions, where gravity warps space-time so severely that our intuitions fail and mathematics becomes necessary guide. China's Tianwen-2 mission, planned for launch in May 2025, aims to collect samples from near-Earth asteroid Kamu-Alewa and study a comet. Kamu-Alewa is quasi-satellite of Earth, meaning it orbits Sun but stays close to Earth, roughly 40 to 100 meters in diameter. Some scientists theorize it might be fragment of Moon, ejected by ancient impact event. Sample return will help confirm or refute this hypothesis. mission demonstrates growing sophistication of China's space program. Advancing from lunar missions to asteroid sample return, multiple nations now have capability to explore beyond Earth-Moon system, democratizing space exploration. Ensuring future of space travel doesn't depend on single nation, but represents collective human endeavor involving all our species. International cooperation and competition both drive progress, pushing boundaries of what's possible. Vacuum of space isn't complete vacuum, but contains roughly 1 atom per cubic centimeter. That's incredibly sparse compared to Earth's atmosphere, which contains about 2.5 quintillion molecules per cubic centimeter. But space isn't truly empty. Between stars, interstellar medium contains gas and dust, nebulae, where new stars form. Between galaxies, intergalactic medium is even more diffuse but still present. Universe has no truly empty regions. Everywhere contains something, even if just few atoms, photons from ancient light, neutrinos passing through without interaction. Space is vast and mostly empty, but emptiness itself is fascinating, raising questions about nature of vacuum, quantum foam, virtual particles constantly appearing and disappearing from nothing. Quantum mechanics suggests even perfect vacuum seethes, with activity at smallest scales, temporary fluctuations in energy fields, particles popping in and out of existence. Space, in deepest sense, is never truly empty, always contains potential, possibility, subtle energy that underlies all reality. You might be feeling tired now. That's perfectly fine. Breathe slowly. Feel the cycles. Spacecraft orbit Earth. Earth orbits Sun. Sun orbits center of Milky Way. All are circles, cycles, endless orbits. Like your breath. Inhale, exhale, inhale, exhale. A small cycle within vast universe. You are also part of that eternal movement. You don't need to hold on to anything. Let everything unfold in its perfect order, like planets silently rotating in their orbits. Unhurried, unresisting, simply existing. We're almost there now. Stars are not eternal. Every star you see in night sky is slowly burning through its fuel, fusing hydrogen into helium in its core, releasing energy that makes stars shine. Small stars burn slowly, living trillions of years. Massive stars burn fast, exhausting fuel in mere millions of years, then exploding as supernovae. Our Sun, medium-sized yellow star, has burned for 4.5 billion years and will burn for perhaps 5 billion more. Eventually, Sun will swell into red giant, consuming inner planets, then collapse into white dwarf, cooling slowly across eternity. Silence in space is absolute. Sound requires medium to travel through, air or water or solid material. In vacuum, there are no molecules to vibrate, to carry sound waves from one place to another. Explosions in space are silent. Rockets fire without thunder. Collisions happen without crash. Astronauts communicate through radios, electromagnetic waves that don't need medium. The silence feels almost holy to those who've experienced it. Profound emptiness, broken only by sounds from within spacesuit, breathing, heartbeat, reminders that life continues even in void. Light takes time to travel. even at its tremendous speed. Sunlight reaching Earth is already 8 minutes old, showing us Sun as it was 8 minutes ago, not as it is now. Light from Jupiter takes 40 minutes to an hour, depending on orbital positions. Light from nearest star beyond Sun, Proxima Centauri, takes 4 years to arrive. Looking at distant galaxies, we see light that traveled for millions or billions of years, showing universe as it was in distant past. Astronomy is time travel, looking back across space and time simultaneously. Neptune, farthest planet from Sun in our solar system, takes 165 Earth years to complete single orbit. It was discovered in 1846 and has completed only one full orbit since then, returning to its discovery position in 2011. From Neptune, Sun appears as bright star, still brightest object in sky but tiny, no longer recognizable as disk. Temperatures plunge to -200 degrees Celsius. Dark, cold, distant. Neptune reminds us, solar system extends far beyond warm inner planets where humans evolved. Space is vast beyond everyday comprehension. Titan, Saturn's largest moon, is only known moon with substantial atmosphere, thicker than Earth's. This atmosphere is mostly nitrogen, like Earth's, but surface temperature of -180 degrees Celsius means water freezes solid as rock. Instead, Titan has lakes and rivers of liquid methane and ethane, hydrocarbons, that remain liquid at these frigid temperatures. Titan's weather includes methane rain, possibly methane snow. Its alien world with weirdly familiar processes, hydrological cycle like Earth's, but using different substances. Someday, humans might visit Titan, exploring its orange haze-shrouded surface. First photograph of Earth from space was taken in 1946 by V-2 rocket reaching 100 kilometers altitude. Black and white image showed Earth's curved horizon, clouds below. Since then, countless images have been captured, but one stands out. Pale blue dot, taken by Voyager 1 in 1990 from 6 billion kilometers away, shows Earth as tiny point of light, barely visible against darkness. That image inspired Carl Sagan's famous reflection on humanity's place in cosmos, our home suspended in sunbeam. Magnetic fields can be visualized by their effects on charged particles. Earth's aurora, northern and southern lights, result from solar wind particles following magnetic field lines toward poles, colliding with atmosphere, causing it to glow green, red, sometimes purple. Jupiter's auroras are even more spectacular, powered by its immense magnetic field. Charged particles trapped in Jupiter's magnetosphere spiral along field lines, creating permanent auroras far brighter than Earth's. Wherever magnetic fields exist, they shape how charged particles move, creating patterns of invisible force guiding matter through space. Pluto was considered ninth planet until 2006, when astronomers reclassified it as dwarf planet. Pluto is small, smaller than our moon, orbits in region of solar system called Kuiper Belt, filled with icy bodies left over from solar system's formation. New Horizons spacecraft flew past Pluto in 2015, revealing heart-shaped glacier, mountains of water, ice, possible subsurface ocean. Pluto is far more interesting than mere frozen rock. Distant, cold, beautiful, Pluto represents frontier of our explored solar system, boundary between known and mysterious. Spacecraft carry golden records, time capsules for potential alien civilizations. Voyager 1 and Voyager 2 each carry identical golden records containing sounds and images from Earth, greetings in multiple languages, music from various cultures, photographs showing human life and landscapes. Records are designed to last billions of years, potentially outliving Earth itself. If alien civilization ever finds Voyager, they'll discover this record. Message from humanity saying we existed. We created art. We wondered about universe. We reached out hoping someone might answer. Moon is gradually moving away from Earth, about 3.8 centimeters per year. This happens because tidal forces between Earth and Moon transfer rotational energy from Earth to Moon's orbit. Billions of years ago, Moon was much closer, looming larger in sky, causing more extreme tides. Billions of years in future, Moon will be even farther, appearing smaller. Eventually, Moon might escape Earth's gravity entirely, though this will take tens of billions of years, long after Sun has died. Everything changes slowly, imperceptibly, across deep time. Oxygen we breathe was created by ancient cyanobacteria billions of years ago. Before then, Earth's atmosphere contained no free oxygen. These tiny organisms used photosynthesis, splitting water molecules, releasing oxygen as waste product. Over hundreds of millions of years, oxygen accumulated in atmosphere, fundamentally transforming planet, enabling evolution of complex aerobic life, including animals. We breathe, waste, product of bacteria, ancient gift from microscopic organisms that changed world. Every breath connects us to distant past, to origin of life itself. Comets are frozen remnants from solar systems formation, dirty snowballs of ice and rock orbiting Sun. Most comets remain in distant Oort cloud, but occasionally gravitational perturbations send comet falling toward inner solar system. As comet approaches Sun, ice vaporizes, creating glowing coma and tail stretching millions of kilometers. Comets reminded ancient peoples of mortality, omens appearing without warning. Today, we understand comets as time capsules, pristine samples of material from which planets formed, carrying clues about solar system's earliest days. Your brain creates entire worlds while you sleep. Every night, during REM sleep, your mind constructs vivid experiences from memory fragments, emotions, and abstract patterns. Characters appear, conversations unfold, and landscapes emerge, all generated from within. These dream worlds feel real in moment, complete with sights, sounds, and even physical sensations. Yet they vanish upon waking, like morning mist. The sleeping brain is not resting, but creating, exploring possibilities that waking life never offers. Dreams remind us consciousness is stranger, more malleable than everyday experience suggests. Water exists in three forms: solid ice, liquid water, gas vapor, but it can exist in unusual states too. In space's vacuum, water ice sublimes directly to vapor without melting. Under extreme pressure, Multiple exotic forms of ice exist, some remaining solid at hundreds of degrees above normal freezing point. Water's unique properties: its ability to dissolve many substances, its expansion when freezing, make it essential for life as we know it. Life arose in water. Life needs water. Life is mostly water. Mercury, closest planet to Sun, has strange relationship with time. It orbits Sun every 88 Earth days, but rotates on axis only once every 59 days. This creates bizarre situation where Mercury's solar day, the time from one sunrise to the next, lasts 176 Earth days, twice as long as its 88-day orbital year. Standing on Mercury, you'd see sun rise, move across sky, stop, move backward briefly, then continue forward, all in slow motion over months. Time and motion work differently there, reminding us familiar patterns don't apply everywhere. Night sky appears black because universe, though filled with stars, is also expanding. Light from most distant galaxies has been stretched by expansion into infrared wavelengths our eyes cannot see. Additionally, finite age of universe means light from most distant objects hasn't had time to reach us yet. Darkness of night sky, paradox that puzzled astronomers for centuries, is evidence for universe having beginning, for space itself expanding, for vastness beyond what light can cross in universe's lifetime. Fusion reactions in stars forge heavier elements from lighter ones. Hydrogen fuses into helium, helium into carbon, carbon into oxygen, continuing up periodic table. Iron is where process stops. Fusing iron requires energy rather than releasing it. Elements heavier than iron are created only in supernovae, violent stellar explosions, providing energy needed for these reactions. Gold, platinum, uranium, all were created in dying stars, scattered into space, eventually incorporated into planets including Earth. Every heavy element you've ever touched came from exploded star. Moons are common throughout solar system. Earth has one. Mars has 2 tiny moons. Jupiter and Saturn have dozens each, some as large as planets themselves. Moons form through various processes. Some coalesced from disk of material orbiting planet. Some are captured asteroids. Some formed from debris after giant impacts. Earth's moon likely formed when Mars-sized object collided with early Earth, ejecting material that coalesced into moon. Studying moons reveals how planetary systems evolve, how gravity shapes orbital relationships across billions of years. Neutrinos are ghost particles, passing through matter without interacting. Trillions of neutrinos from Sun pass through your body every second, continuing through Earth, emerging on other side, unaffected. They're products of nuclear reactions in stellar cores. Detecting neutrinos requires massive underground detectors, waiting for rare occasions when neutrino actually interacts with atom. Studying neutrinos lets us see directly into star cores, otherwise hidden beneath layers of plasma. Neutrinos are universes, secret messengers, carrying information from places light cannot reach directly. Spacecraft power comes from various sources. Near Sun, solar panels convert sunlight into electricity, but distant spacecraft like Voyager use radioisotope thermoelectric generators, powered by heat from radioactive decay of plutonium. These generators provide steady power for decades, enabling exploration of outer solar system where sunlight is too weak for solar panels. Future missions might use small nuclear reactors, providing more power for advanced propulsion systems, powerful transmitters, active thermal control, enabling missions currently impossible with existing power sources. Orbital mechanics follows precise mathematical laws. Planets orbit Sun in ellipses, not circles, moving faster when closer to Sun, slower when farther. These patterns, described by Kepler's laws 4 centuries ago, emerged from careful observations, were later explained by Newton's gravity, further refined by Einstein's relativity. Every spacecraft trajectory is calculated using these principles, paths determined months or years in advance, accounting for gravity of every nearby body. Spacecraft follow these invisible curves through space with ballistic precision. Hubble constant describes how fast universe expands. Space itself stretches, carrying galaxies apart. Galaxies aren't moving through space, but space between them is growing. Farther galaxies recede faster, not because they're moving faster, but because there's more expanding space between us and them. Eventually, most distant galaxies will recede faster than light speed, not because they're traveling through space faster than light, which relativity forbids, but because space itself expands. Universe grows larger every moment, making cosmos vaster than we can ever explore. Moon has no atmosphere, no weather, no erosion beyond meteorite impacts. Footprints left by Apollo astronauts over 50 years ago remain pristine, undisturbed. They'll persist for millions of years unless meteorite happens to strike exactly there. In airless environment, nothing moves without being pushed. Flags planted by astronauts remain where placed, though radiation from Sun has likely bleached them white by now. Moon is museum of exploration, preserving evidence of every visitor across geological timescales. Looking at stars, you're looking back in time. Light takes years to reach us from nearest stars, centuries from farther stars, thousands or millions of years from distant nebulae and galaxies. When you gaze at night sky, you're seeing universe as it was across vast spans of time. Some stars you see might have already died, their light still traveling across space, not yet informed us of their demise. Night sky is living history book, pages written in starlight. Space travel reminds us how small Earth is, how vast universe is, how remarkable life is. From space, national borders vanish, conflicts seem petty, human divisions meaningless. We're all passengers on this pale blue dot, floating in sunbeam, only home we've ever known. Exploring space doesn't diminish Earth, it makes us appreciate it more. Every distant world we study highlights Earth's uniqueness. Every hostile environment emphasizes Earth's hospitality. Space travel, ultimately, helps us understand home better, see our world with new eyes, cherish what we have, and so, our quiet journey through space travel comes to gentle close. We've traveled from violent rocket launches tearing through atmosphere to silent glide of spacecraft through void. From astronauts floating weightlessly to stars burning steadily across billions of years. Discovering along way that universe is both vast beyond comprehension and intimately connected. From explosive thrust of chemical rockets to whisper soft push of ion engines, from fragile biology, transforming in microgravity to resilient human spirit, reaching beyond all boundaries, we've glimpsed how space travel is both struggle and triumph, danger and wonder, endings and beginnings all intertwined. Space travel reminds us that exploration is fundamental human need, written into our DNA by ancestors who crossed oceans and continents before we dreamed of crossing space. Much of the universe remains beyond our reach, hidden in darkness. Separated by distances light takes years to cross, in silence so absolute that sound itself cannot exist. Yet spacecraft we build, fragile and temporary, carry human hope outward. They teach us patience, resilience, interconnection. Without curiosity driving us forward, without courage pushing us through fear, without cooperation joining our efforts, wed, never venture beyond familiar skies. By pausing to notice, we glimpse extraordinary in ordinary, simple fact that you're here, conscious, aware, breathing rhythmically, is itself remarkable beyond words. And now, in these final minutes, take the deepest breath you can, as deep as possible. Think about unity of every atom, every event, every moment in universe. You are not separate. You are link in endless chain. Think about how spacecraft orbit Earth. Earth orbits Sun. Sun orbits center of galaxy. All movement, all existence, connected in dance, billions of years old. You too are part of that flow, that cycle, that eternal return. Let your entire being dissolve into gentle darkness, into soft gravity, pulling you into sleep, into space before thought. Prepare for deep sleep, no boundaries left, only peace. If this gentle journey through space travel brought you peace tonight, perhaps share it softly with someone else who's searching for stillness under stars. It might be exactly what another restless mind needs to finally let go and drift. One quiet share, one peaceful night at a time. But there's no need to do anything now. Nothing at all. You've traveled far tonight, farther than most journeys take you. You can allow these thoughts of space travel to fade now, like stars dimming at dawn, leaving only peaceful calm behind. Let your breathing deepen. Let your body feel heavier, as if Earth's gravity has found you again after long absence, gently pulling you down toward rest. If sleep comes, let it carry you like spacecraft drifting through darkness, smoothly, inevitably, into realm where time and weight no longer matter, where dreams replace facts and peace replaces thought. If your eyes are still open, the next video is waiting for you, ready to continue journey. But if they're closed, stay there. Stay in darkness that feels safe and warm. Stay floating in that space between waking and sleeping, that boundary where consciousness softens and lets go. Tomorrow, spacecraft will still orbit, stars will still burn, universe will continue its slow expansion. But tonight belongs to stillness. Tonight is yours to rest. Rest well, sleepy scientist. And remember, we are all space travelers, riding this beautiful planet through infinite dark, together beneath same stars, sharing same wonder, breathing same ancient air. Fall asleep to gentle facts. Dream deeper with bedtime science. Good night.